Maybe there's a function u of x, y, such that when I take the total differential and I get this, it's exactly the differential equation m dx plus n dy equals 0. Why is that good? Because if this equation, if the m dx plus n dy is just basically du, then what happens? The differential equation then comes out to be just du is equal to 0, and that implies that u, which would be a function of x and y, is equal to a constant. And you've integrated the equation. Okay? So we have to find out, when does that happen? Right? Okay, everybody get the idea? The essential idea is this is the most important thing to understand. You've got the differential equation in this form, and suppose that we can come up with a nice test that tells you, oh yeah, if this conditions are satisfied, then this m dx plus n dy is nothing more than the total differential of some function u. Then the differential equation becomes du equals 0, and we know how to integrate du equals 0 to u equals constant. Okay. So the first part I'm going to do is the necessary condition, part 1. Okay? Let's assume m dx plus n dy is exact. What does that mean? i.e., there exists a function u of xy such that the differential of u is basically the differential equation m dx plus n dy. And remember, m and n are functions of x and y. Okay? So we're saying now, suppose that we know by some method, but we know somehow, okay, and we'll find out how that somehow is a test that we'll find out how to do. But suppose that someone tells you, yes, this differential equation you have m of xy dx plus n of xy dy. The left-hand side of that is the differential of some function u. Okay? Suppose that happens. Then is there some consequence of that? And the answer is yes. Because you know, what does that mean? Therefore, m dx plus n dy, what's the total differential of u? It's right over here, right? So that equals partial u partial x dx plus the partial of u with respect to y dy. Now, in this thing, we're in the setting of independent variables. X and y are independent variables. The only way this and this can match for all values of x and y in a certain region is if the dx and the dy coefficients are equal. And therefore, a consequence is partial u partial x has to equal this function m of xy, which you know, and partial u partial y has to match the dy coefficient, which is n of xy. Okay? And you recall from your calculus that we have second order partials. The order of differentiation does not matter provided the derivatives are continuous. And all the stuff that we're going to do is going to be continuous. So let's take this partial of this guy with respect to y. So we know this equals this equals this. Differentiate this guy with respect to y. You have the second partial u with respect to y, with respect to x, equals, partial of m with respect to y. Okay? Similarly, taking this and differentiating both sides with respect to x, we have the second partial of u with respect to x with respect to y equals the partial of n with respect to x. Provided that what? These mixed partials are continuous, or equivalently, provided that the m dy and dn dx are continuous. Okay? So I'm going to put this kind of in red over here. Okay? I think we can go over here. Okay? So that's like a test that we have, right? If it's exact, these two equations have to be true. So therefore, if that doesn't follow, right? If dn dx is not equal, that's right. I skipped a little. Okay. So you got this, right? So look at this. Oh, here we have the second partial with respect to y with respect to x. Here we have the second partial with respect to x with respect to y. From calculus, we know that the order differentiation does not matter. Okay? Just try it if you don't believe it. Okay? you have a function u of x, y, and these mixed partials are continuous, it doesn't matter if you differentiate first with respect to x and first with respect to y, as we did here, or you differentiate first with respect to y, then with respect to x. So therefore, we must have the partial of m with respect to y equals the partial of n with respect to x. Okay? So, let's just write that down because it's an important result. So, if m of xy dx plus n of xy dy is exact. Again, what I mean by exact, that's just the total differential of some scalar function u. Then we must have partial m partial y equals the partial of n with respect to x. Now be careful over here, okay? You have to remember that the original equation was m dx plus n dy equals 0. I take the partial of the dx coefficient not with respect to x, but with respect to y. And similarly, I take partial n, not partial n partial y, but partial n partial x. Okay? So we have here basically what's called a necessary condition. Yeah, if the left-hand side of your differential equation happens to come out to be the total differential of some function u of x, y, then this condition must be satisfied. So what does that tell you? If you're given the differential equation, you know m of x, y, and you know n of x, y. Okay? So you just crank out the partial of m with respect to y, the partial of n with respect to x. If they're not equal, it's not exact. So this method that we're going to develop does not work. But what we haven't shown is the following. Just think about it. We showed over here that if m dx plus n dy is exact, you have to read very carefully. If this is true, then this condition holds. But in practice, you don't know that. You want to go the opposite, right? You want to test saying that, oh, maybe it'll happen that if this test holds, then it's exact. And that's what we have to prove. Because that's what you can do in practice, right? You're given the functions m of x, y, and n of x, y, and no one's going to, no angel from heaven is going to come down and say, oh, that's exact, by the way. You have to figure it out yourself. So it requires a proof now, okay? And what we'll have then is what's called a necessary and sufficient condition, which is very nice. In other words, if it holds, it's exact, and conversely, if it's exact, it must hold, okay? Now this proof is going to be a little involved, okay? But you should pay attention to it because the steps that I'm going to do in the proof are going to mimic what we do in examples, okay? But don't try to memorize anything here. Let's just follow it through and see what happens. Okay. So now I'm going to go over here, okay? So I start off now with the differential equation m of xy dx plus n of xy dy is equal to 0. Okay? Now notice over here how I started. I said, let's assume it's as exact, and we get this. I want to try to prove the converse of that. So I got the differential equation, and now suppose, and this is something you can definitely crank out, right, and you can test it, right? Suppose that in a certain region of the xy plane, partial m partial y equals partial n partial x. In a region of the xy plane. Let's say in a region, it's a region of the xy plane. Okay, suppose, and that's easy, right? You're going to know m, you're going to know n, just crank out the derivatives, and well, this thing, yes, it's an identity. I suppose that's true in the region of the xy plane. What do we want to do now? Show that this equation is exact. What does it mean it's exact? Show that there exists a function u whose total differential is given by that. Okay? Show that m dx plus n dy is nothing more than the differential of u. And again, why is that really good? Because now this complicated expression is replaced by du equals 0, and then u equals constant is the solution. Okay. So show that m dx equals plus n dy equals du. Or, what amounts to the same thing, show that you can find a function u of x, y that satisfies these two equations. Partial u partial x equals m, right? And partial u partial y is equal to n of x1, right? because that's what the differential of u is, right? Look at it, right? It's du dx dx, and then du dy dy. So the problem that you can have in any given equation is you'll know this is a function of x and y. You know this is a function of x and y. And what I want to show you basically is that if it's exact, okay, if this condition is satisfied, you can always get a u function that satisfies both of these. Okay? Now how would we go about doing that? This is why I went over partial integration just a second ago. Not a second ago, at the beginning of the class. Let's take this guy, it doesn't matter which one. Let's start with this, and let's see if we can actually find a u that satisfies that. U equals what? I have to integrate with respect to x. But remember, it's a partial derivative. So u is the integral of m of xy dx. And remember, this is a partial integration. When you do this, you make believe y is fixed, and you integrate with respect to x because it's partial u partial x. Very important to understand that. It's not du dx in the normal sense. It's a partial derivative. Okay? Plus now, what do I get? I get an arbitrary function of y. Right? Just check it. Partial u partial x, well, that gives me m. And since that's a function of y only, okay, the derivative with respect to x, that will be 0. Okay. Now, I'm almost there, but I have to find phi of y. Well, I have another piece of information. Partial u partial y has to equal m. Okay? So let's calculate the partial of u with respect to y. Okay? That's the integral. I bring the d by dy inside. Partial m partial y dx plus phi primed of y. Okay? And be very careful now. Phi of y is only a function of y, so this is the normal d phi dy. That's only a function of y. Okay? But I know partial u partial y. That has to equal n of xy. Okay? Let me just write this in a different form for you. We can take this, solve this with d phi dy. Give the derivative phi with respect to y equals what? On the right-hand side, we got n of xy, right? Minus the integral of partial m partial y dx. Okay. Now, let's look at this, just the structure of this equation. Okay? N of xy is a function of both x and y. Presumably, partial m partial y is a function of x and y. When I integrate respect to x, it's also a function of x and y. So it looks, oh yeah, we have a problem. Because the right-hand side in general looks like it appears to be a function of both x and y, and the left-hand side can only be a function of y. Okay? But what I'm going to show you is that the right-hand side is independent of x, which then basically means it's only a function of y, and then you can integrate again and find phi of y. Okay? Everyone understand the logic over here? Okay? It looks like the right-hand side is a function of x and y. But that's not going to work out then because here I have a function only of y. So the only way that this will make sense is if the right-hand side is independent of x, or its x partial is equal to 0. Okay, so must show right-hand side independent of x. What's the easiest way to find that something's independent of x? Take its partial with respect to x and show it goes to 0. So the partial with respect to x of the right-hand side is equal to what? We got partial n partial x, right? Minus the partial derivative with respect to x of the integral of partial n partial y dx. Okay. That's 0. Well, now I'm going to use this condition. This is the whole key, right? We started off, we assumed at the beginning that the m dy equals dn dx. So let's look at that. But partial m partial y is equal to the partial of n with respect to x. That's what I assumed. So therefore, when I do d by dx of the right-hand side, what do I get? I get partial n partial x, right? Minus d by dx of the integral, partial n partial x dx. Okay? Well, if I take partial n partial x, I integrate with respect to x, and I differentiate with respect to x, don't I just get back partial n partial x again? Yes, n equals 0. So it actually happens that the right-hand side is independent of x. Okay? So let me write down the second part, and then we'll give a recipe and do some examples. And we have basically if partial m partial y equals partial n partial x in a region of the xy plane, then the equation is exact. Okay? I think the best thing to do now is to just do some examples. Okay? Okay, so basically what's going to happen in general is you'll start off with an equation like this, okay? You'll test if it's exact or not. You just crank out partial n partial y, partial n partial x. Okay, obviously the problems we're going to do today, that's going to be satisfied. Great, that means it's exact, okay? That means that you know there exists a function u such that what? Partial u partial x is that, and partial u partial y is that. Well then, just like we did in the general proof, we'll integrate one of those, okay? We'll find our phi of y, finally get our u of x and y set to a constant, and that'll be the solution to the equation. Okay? So the whole key is basically this thing. It's called a test for exactness. Okay? And of course the question is what happens when that fails? And that'll be a topic for later on. But let's make sure we can do these type of problems first. Okay. Maybe I should just wait for questions because I think the best thing is to see an example. Okay? So here's example number 1. Okay? And these equations can become very messy as well as the solutions. They usually come, remember I said that, I think the first or second lecture I talked about different types of differential equations. And I said sometimes you'll get an explicit solution where you can write y in terms of x. Many times there'll be some hideous function of x and y equals 0, and you can't analytically solve for y in terms of x, and you have to go to the computer, you have to do it. Okay, so let's start off with the following. 2xy dx plus x squared minus 1 dy is equal to 0. So that's not separable, right? dy dx is not a function of x times a function of y. And recall also that maybe the equation is not given that form. Maybe it's solve that for dy dx. What do you get? You get dy dx is minus 2xy of x squared minus 1, which is a nonlinear. You'll have to put it in that form. I'm saving